This time I want to look in particular at second order active filters. Second order meaning that there are two poles in the frequency response, and that in turn means that there is a quadratic equation in the denominator of the frequency response. Now it's perfectly possible to generate second order responses with passive filters. This passive filter, for example, has a second order response. If you go through the algebra of working out what the frequency response is, you'll get this expression here. It's quite a good exercise for a rainy afternoon if you're that way inclined. What you can also show, and is another quite good exercise, is that it is impossible to get a Q factor of greater than a half from this circuit. Now, if you remember that plot of the frequency responses of second order systems that we've seen before, it looked like this. Quite often we want to design our filters for a Q factor of 1 over root 2, because that's the value that gives you the maximum flat region here, with no peaking in the response, before the amplitude response starts to head off down to the high frequency asymptote 40 dBs per decade. And if you want a Q factor of 1 over root 2 from a passive filter, then you have to use an inductor. Simple RC circuits, like the one that we've just seen, won't get there. And inductors are best avoided if you can. They are expensive, and they're difficult to work with because they have large parasitics. Real inductors don't behave much like ideal inductors at all. They also tend to be non-linear. So the value of inductance that you get is a function of the amplitude of the signal that's passing through. And this is where active filters can really help, because it is possible to build an active second order system which only uses resistors and capacitors as well as the op-amp, and yet can have a Q factor of anything you want. The only disadvantages are the usual disadvantages of active filters. The fact that they need a power supply, they'll introduce a bit more noise, and they will limit the maximum amplitude of the signal. So how do you do it? Well, there are actually quite a few different second order active filters. This is a common one known as a VCVS, or a voltage controlled voltage source active filter. You can work out its frequency response using the standard sort of circuit analysis techniques that we've used before. It's a bit tiresome, but it's fairly straightforward if you just follow the general rules. I've called this point in the circuit here X. Therefore, the current flowing through this resistor here is going to be 1 minus X over R. That's just Ohm's law, and I'm working with the phasor representation of the input voltage here, which is just 1. The current through this capacitor is going to be X minus V out divided by the complex impedance of the capacitor, which is divided by 1 over j omega c. In other words, it's j omega c times X minus V out. The current through this resistor here is going to be the same as the current flowing through this capacitor here. No current flows into an ideal op-amp, so the current flowing down this leg of the circuit here is going to be X divided by R plus 1 over j omega c. That's the sum of the complex impedances of these two components. Applying Kirchhoff's current law to this node X in the circuit here tells me that this must be equal to this plus this. The total current flowing into the node X is the total current flowing out of the node X. So I have 1 minus X over R equals X minus V out times j omega c plus, and I'll multiply top and bottom of this expression by j omega c as well to tidy it up a bit. J omega c times X over 1 plus j omega RC. Now, I also have the performance of this op-amp to consider. The voltage on the non-inverting input of this op-amp I can get just from the potential divider equation, this being the potential divider here, and X being the voltage at the top of the potential divider. That would give me the non-inverting input to the op-amp here, I'll call it V+, is X times 1 over j omega c divided by R plus 1 over j omega c. That's just equal to X over 1 plus j omega RC. The op-amp here is configured as a non-inverting amp with a gain of 1 plus R1 over R2. So V out is equal to the non-inverting input, X over 1 plus j omega RC, multiplied by the gain of the op-amp, which is 1 plus R1 over R2 in this case. Then all I have to do is take this formula and substitute in to eliminate X between these two simultaneous equations. And that will give me V out as a function of V in. V in is just 1 in this case. I could have written this as V in the more general case. I won't bother to go through all the rest of the algebra. It gets a bit tiresome. For details, have a look at the short introductions if you really need to know. But the result that you get is this for the frequency response. And if you just compare this to the standard form of a second order frequency response, the gain at dc over 1 plus j omega over q omega naught plus j omega squared over omega naught squared, then you can see that the Q factor times the resonant frequency is going to be 1 over RC times 3 minus R1 plus R2 over R2. And from this term here, we can see that the resonant frequency is just going to be equal to 1 over RC. So that term there will cancel out with that RC, and we're just left with the Q factor is 1 over 3 minus, and we can simplify this one stage further by noticing that R1 plus R2 over R2 is just equal to 1 plus R1 over R2, and 1 plus R1 over R2 is the low frequency gain of the op-amp. So we could write it like this. The Q factor is 1 over 3 minus the gain at low frequencies. Now, for a non-inverting amplifier like this, the minimum possible value of the gain is 1, which means that the minimum possible value of the Q factor you can get from this filter is a half. But there is no theoretical limit on the maximum value of the Q factor you can get. If you wanted a Q factor of 10, that would be reasonably easy. All you'd have to do is set the gain of the op-amp stage here to be 2.9. We can see it in the simulator here. I can change the gain, and you can see that both the gain at low frequencies is changing, because the low frequency gain here is creeping up slightly, but the amount of resonant peaking you're getting at around the resonant frequency is also changing, and we're getting a response characteristic of quite a high Q second order system without any inductors. Just before we leave this circuit, some of you may have noticed that there is something rather odd going on here, or at least potentially rather odd. There would be absolutely no reason why you shouldn't choose the resistors R1 and R2 to give you a gain of 4. And if you get a gain of 4, that suggests that the Q factor is -1. we've built a circuit with a negative Q factor. What does it mean to have a negative Q factor? Well, that's something I will leave to the labs, because in the labs we can actually build this circuit and see what happens. There's another consequence of this formula, which turns out to be quite important as well when you're choosing a circuit for your filter. And that is that the Q factor and the gain at DC, low frequency gain, are determined by the same two resistors, R1 and R2. In other words, you cannot set them independently. Deciding what Q factor you want forces you to have a particular gain at DC. And often you don't want to do that. It would be nicer to have a circuit in which you could set the gain at low frequencies and the Q factor and the resonant frequency all independently of each other. With this circuit, you can't do that. In the next video, however, I will introduce a circuit which can do exactly that, and which is commonly used in real life.